Yes? No issues? Okay. So how are you people doing there? Are we studying nicely or not? Yes. Revising the things. Okay, good. Now the thing is, I think how far we have completed in the last class? I think I have given you one question based on MOT if I'm not wrong. Only for oxygen we have just seen how to calculate, how to calculate that bond order we have seen using the formula. Few more questions are remaining which we are going to do, right? So let us start there, okay? Fine? So let us go for first one. We'll see the shortcut for bond order. And this shortcut maybe majority of you might be knowing, but still, let us see that. All you need to remember here is number of electrons. If it is 14, what is the bond order corresponding to this? Bond order is going to be 3. That much you know already. Hai na? For nitrogen, we already know. For N2. Okay. Now next is any addition or subtraction from here. For each electron added or subtracted from here, what you are going to do is you are going to decrease bond order by 0.5 for each electron added or subtracted from this 14, and always you are going to take it as base as 14, right? So with respect to 14, whenever you are adding or removing electron, per electron you are supposed to subtract 0.5, okay? Now in this case, suppose if I write 15 electron. So basically I've added 1 electron with respect to 14. That means now how much I should subtract? I should subtract only 0.5 from here. So basically I'll be getting bond order as 2.5. Similarly, 14, in fact now 16 because I've added 2. So the bond order still will be reduced by 0.5. Now the thing is you can do directly also with respect to 14 and 16 if you compare. 14 and 16, how much you have electrons you have added? You have added 2 electrons. Per electron you have to reduce 0.5. So 2 into 0.5 is how much? It is 1, right? So you subtract 1 from 3. So that's how you are getting 2. Okay. You have to continue this till what time? Till you have 20 electrons, because bond order here will be 0. Are you able to see what is the difference between 20 and 14? It is 6. Per electron you have to subtract 0.5. So 6 into 0.5 is 3. So 3 minus 3 becomes 0, right? Similarly, if at all I write this as 13, then the bond order equal to 2.5, right? 1 electron I have removed, right? Then again 12. So bond order will be 2. The thing is you identify 14 and 12. How much is the difference? You removed 2 electrons. So you subtract 2 times that 0.5. 2 into 0.5 is 1. So 3 minus 1 is 2. Are you getting that? Now this exercise, till what you have to continue? Till the time, basically, you are reaching the number of electrons as 8, because at 8, bond order is going to be 0, right? Now, if at all lesser than 8 is there, 8 to 20, your problem is sorted out. More than 20 is not in your syllabus, right? Now, the thing is, if number of electrons, they're like lesser than or equal to 8, then you can simply use this, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, because ultimately you just require 4 molecular orbitals to fit in 8 electrons at max. And then you can simply calculate bond order is NB minus NA by 2. That's how you do, right? Quickly note this down and then we'll see one question. And once you are done writing, let me know. Okay, now I am giving you one question. Write the configuration of O2 and C2. Find the number of sigma and pi bonds present in them. Find the number of sigma and pi bonds present in them. Do it. Then we'll discuss this. For O2, number of electron is 16. You will be writing sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px equal to pi 2py. Then you are having pi star 2px equal to pi star 2py. Now here 1 electron. So I hope 16 are done. 1, 2, 3, 4, 5, 6, 7, 14, 15, 16, right? Now the thing is, when we have to identify how many bonds are there, right? Sigma bonds and pi bonds we are talking about. Similarly, I'll just write down for C2 also. C2 is 12 electrons. So you're going to write down sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px equal to pi 2py. So we're having 2, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Now the thing is, you identify here. For each molecular orbital set, either you can calculate their bond order and identify whether any bond exists or not, or else you can think of like this. You are having sigma 1s here and you are having sigma star 1s here, right? So basically, whatever bonding is happening because of sigma 1s, it is being cancelled here, right? So basically, no bond here. That means I could have calculated bond order only for this particular molecular orbital, right? Antibonding and bonding both have to be considered. So in this case, I could have written number of electrons in bonding is 2, antibonding 2. So you are having 0 here. Similarly, this also, there is no kind of, no bonding here. What about sigma 2pz? First of all, it is telling you that it is sigma molecular orbital. So giving you an indication that sigma bond is getting formed. And how many electrons are required for the bond formation? One bond formation, only 2 electrons. So are you getting to know that there is one sigma bond here, right? So I'll be writing one sigma bond. Or else I could have calculated the bond order. Now the thing is, in sigma star 2pz, there is no electron. I have not written it, but there is no electron which is going there, right? So basically, number of electrons in bonding is 2, antibonding 0. So basically, did you get 1? Is it identifying with the result? Now, what about this? You try to understand it. The entire pi molecular orbital, its bonding as well as antibonding you have to consider, right? Now in this case, if you look at pi molecular orbital, there are 4 electrons, right? 4 electrons means it is telling you there are 2 bonds. And which kind of bond? Pi bond. Because you are having electrons in this pi molecular orbital, okay? So we got to know that there are 2 pi bonds, but you are able to see pi star 2px and pi star 2py. That is also anti-bonding pi molecular orbital, right? So there again 2 electrons are there. So 2 electron means 1 bond. So out of 2 bonds, 1 bond is getting cancelled. That's what is because of the anti-bonding electrons there, right? So basically we are going to have only 1 pi bond. If at all you are not able to judge like this, then what you can do is, you can calculate the bond order here. Simply NB minus Na by 2. I'm just taking the set of this pi molecular orbital. That means it's bonding as well as anti-bonding. Okay. So here how much will be there? In bonding it is 4. In anti-bonding it is 2. Did you get 1? That's how we find out. Please identify the second one. And here itself I'll tell you one small thing. The thing is, you can also write down this configuration as KK and then sigma 2s2, sigma star 2s2, like that it goes on. What is this KK is telling you? This is closed K shell configuration. That means, you know, na, K, L, M, N, like that. So first shell, K shell, right? So sigma 1s2 K. For this one also sigma star 1s2 K. Closed K-shell configuration, we say, right? Getting it? Okay. Now what about this? Here, no bond. Here also no bond. Here, you are having 2 pi bonds. There is no sigma bond here, right? You could have calculated or identified using this also. 4 minus, you are having basically 0. No electrons in antibonding because I have not mentioned also, right? So are you able to relate that MOT supports that without the existence of sigma bond also you can have pi bond? Clear about this, everyone? Understood? Yes? Okay. Can we proceed further? I am giving you one question now. Arrange the following. Arrange the following in decreasing order of the property mentioned. Okay. Now let us say I am going for the first one, which is O2, O2 plus, O2 minus, O2 minus 2, and I am asking you for the oxygen-oxygen bond length. Now here, mind well, the examiner either can give you O2 plus or else they can also mention like this O2 ASF6. They can also give this as or KO2. Try to understand what is the meaning of it. You're able to see arsenic belongs to group 15. If at all it is only making 5 bonds, then the formal charge would have been 0 on this. But it is making 6 bond, right? So when we calculate the formal charge, do you remember we used to break it like this in between, and how many electrons around arsenic? It is basically 6. How many should have been in its valence shell? Basically only 5. So there is one extra. We used to put -1 formal charge here, right? That's how we used to do, right? Now the thing is, this means what? It is AsF6 minus. So definitely for electrical neutrality, it has to be O2 plus. So the examiner can also give you like this. Okay. Here you know that it is K plus and O2 minus. Getting it? Now please do all of them. Then you are having basically N2, N2 plus and N2 minus. You have to go for the stability order. Please solve them. I'm giving you some time. Please solve them. You can very well apply the shortcut for the bond order here so that you are able to quickly calculate them. Hopefully people would have done it. See, in case of O2, how many electrons I am having? 16 electrons. Now if at all you have to calculate the bond order. So bond order is always with respect to 14 you see. With respect to 14 you added 2 electrons. That means you have to now reduce how much? 2 times 0.5. That means 2 into 0.5 is 1. So 3 minus 1, you will be writing bond order as 2. Right? Now next is suppose O2 plus. It is 15 electrons. So what you are going to write down? Bond order is going to be, it is going to be 1.5. Yes or no? Because the thing is, with respect to, sorry, not 1.5 here, it will be 2.5. See, with respect to 14, how many electrons you have added? 1 electron you have added, so you have to just subtract 1 time 0.5. So that is the reason it will be. Now, next I am giving you suppose O2 minus. How many electrons? 17 electrons. So with respect to 14, you have added 3 electrons. So you have to reduce 0.5 3 times. That means 3 into 0.5 is 1.5. So from 3, you reduce 1.5. You are going to get bond order here as 1.5. O2 minus 2, you are having 18 electrons. Right? In this case, basically, when you are having 18 electrons, how many electrons you have added with respect to 14? 4 electrons. So 4 times you have to reduce 0.5. That means 4 into 0.5 is 2. Right? So 3 minus 2, you are going to get bond order as 1. Now you have to go for this bond length order. So do you remember we have written one important point that bond order is inversely proportional to bond length. So in that case, you are going to have O2 minus 2. After that, O2 minus. After that, you are having O2. And in the last, you are having O2 plus. That's how we calculate. Okay. Now, hopefully people would have done it correctly. In case of N2, there are 14 electrons. So straight away I can write down that bond order is 3. In case of N2 plus, number of electron is 13. So simply I can reduce 0.5 from here. So I am having 2.5. Similarly, I am having N2 minus. Here again you are having how many electrons? 15 electrons. So the bond order again here is 2.5. Now, few of you might have written like this. I think maybe majority of you. N2 greater, N2 plus equal to N2 minus. Mind it, this is wrong. You cannot write like this. Do you remember we have written one note also that if at all if bond order is same, then check for which species is having more number of electrons in antibonding, right? So you have to write down for N2 plus. N2 plus is how many? 13 electrons. So basically you'll be writing sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. You are having pi to px equal to pi to py. Then you are having sigma 2pz. So how many electrons here? 13. 2 to 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now what is the bond order here? NB minus NA by 2. So all without star. 2 to 4, 5, 6, 7, 8, 9. 9 minus you are having 4 divided by 2, right? Similarly, you go for writing N2 minus. N2 minus is 15 electron. You are going to have sigma 1s2, sigma star 1s, sigma 2s. You are going to have sigma star 2s, pi to px equal to pi to py, sigma 2pz. And then you are having pi star 2px equal to pi star 2py. So basically 2 to 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and you are having 1 here. And basically when you go for calculating the bond order, NB minus NA by 2, you will be getting here 10 minus 5 upon 2. Now which one is having more number of electrons in antibonding? It's N2 minus. So more the number of electrons in antibonding, lesser will be the stability, right? So basically what is now overall stability order which I have got? N2 maximum because bond order is maximum, then N2 plus and then N2 minus, right? Be sure that you are sticking to all these rules, okay? So whenever you are getting bond order same, please make sure that you are writing the configuration once and you are identifying like this. Getting it? Understood everyone? Okay, fine. Now let us go for the next. Now MOT is completely over. We have seen what are the kind of questions which could be asked from this, right? They can ask you about the bond order. And see, one more thing is, sometimes they can also give you heteroatomic molecule like CO, NO, NO plus, CO plus, right? So if at all they're asking you to calculate their bond order, simply count the number of electrons in them and identify which particular, suppose it is 14, then you have to apply for N2. If at all it is 15, then you have to apply for greater than 14, that particular order. Is that clear? Right? Now let us go for bond energy or bond dissociation energy. I think this particular thing was remaining one bond parameter. So let us take it now. Now, how do I define this? Basically, suppose if I am writing H2, right? I can write like this also. That means heterolytic fission. And I can say that delta H for this is bond dissociation energy. Or else I can also write like this. You have to identify which one is correct, first or second. I could have written in both the ways. I'll say that this is not the correct way, this is the correct way, this is the correct way. So what you're able to see here is, are you able to see I'm breaking the bond here, right? So the minimum amount of energy required to break 1 mole of the bond, right? 1 mole of the bond means when I'm referring to 1 mole of bond, I'm talking about 1 mole of single bond, 1 mole of double bond, or else 1 mole of triple bond, right? Into, are you able to see I've broken it into its constituent gaseous atoms, right? And which kind of fission we have taken? We have taken the homolytic fission, and we have not gone for the heterolytic. If it is heterolytic, you will be getting the ions form, right? So we are going to write here the definition part of it. The minimum energy required to break 1 mole of bond into its constituent gaseous atoms by homolytic fission. By homolytic fission is known as bond dissociation energy, or else simply bond energy also, right? It's relatively more easier to relate with something we are dissociating, है As such, bond energy is a generic term. That means when the bond will be formed, that much amount of energy will be released, and for breaking the same bond which got formed, you have to supply that much of amount of energy, right? Please write this down, then we'll see what are the factors which affect bond dissociation energy. Okay, hopefully people might have written this. Let us go for factors affecting bond dissociation energy. Now the first factor which is there, it is the factor of size. So we say generally size increases, that means bond length is going to increase, and hence bond dissociation energy or the bond energy is going to decrease, right? But I've written the general word, and whenever we are using general word in chemistry, something else you might be expecting. Some species might not be following the trend. Okay. Now here, if at all I'm writing HH, CH, NH, CC, NN, OO, and FF, right? Basically, are you able to see here size is like between this is 1s, right? Because of that overlapping, you are having 2p, 1s, here also 2p, 1s, and for all of them, is it 2p, 2p or not for all of them? Now you remember we checked the size by the principal quantum number. So it is 1, 1, it is 1, 2, and it is 2, 2. So the size is increasing here. If I go like this, size is increasing. And because of that, bond length also increases. And I say that is a weaker bond. So basically bond energy should reduce, and it is following the trend. There is no problem. Only thing here is for OH and FH. Even though they are 2p, 1s, then also they are like maximum here. Reason being, the electronegativity difference is very high. And because of that, what is happening? More polarity, more attraction between them. And to break such attraction, I need to supply more energy. So the bond energy increases. Okay. So please write down this quickly. And once you are done writing, let me know. So do remember, it is only for them I'm saying, you know. Okay. Now, next one is second factor which we need to see is bond order. With respect to bond order, what do we say? If bond order increases, then bond energy decreases, or else it should increase. It should increase because it is more difficult to break a double bond than a single bond, and it is more difficult to break a triple bond than a single bond or a double bond, right? Now, suppose I am writing here C triple bond C, C double bond C, C single bond C. So if at all I ask you about the bond energy, this is going to be maximum because bond order 3 here, 2 there. Similarly, N triple bond N, N double bond N, and N single bond N. You are having the same order for the bond energy here. Now there is one note which I am going to give you here, that we say for bond energy, the factor of bond order dominates size. That means suppose if I mention something like C triple bond C, N triple bond N, and O double bond O, and I have given you HH. If you are able to see, it is 1s, and definitely here 2. Second shell is getting involved, right? Even though here are you able to see that bond order is high, here bond order is less, and because of that fact, the bond energy of this multiple bonded ones, that is more than the size factor of hydrogen. So for bond energy, this bond order is the dominating factor. Please write this down, then we'll proceed further. Hopefully written now. Let us go for the third factor, which is delta En. So if delta En increases, you know what is going to happen? Bond energy is going to increase. Suppose I am taking the example of FH, OH, and NH, right? Now, are you able to see when I am moving from here, for all of them bond order is 1, which is same. And here nature of bond is also same. When I say nature of bond, basically what is happening is you are having different elements which are connected to the same atom. So it's the nature of bond is same. We are reading about XH kind of thing. X is only varying. Fluorine, oxygen, nitrogen. So are you able to see if delta En increases, then in that case bond energy is going to increase. Right? So that's what is the bond energy order. Okay. Another factor is you are having percentage S character. So first write down this factor, then we'll proceed further. Hopefully it is clear to all of you. Now when it comes to percentage S character, if the percentage S increases, we say that the orbital size will decrease, no? Because more like S. So in that case, size decreases. So what is happening to the bond length? it is going to decrease, and hence the bond energy is going to increase. Right? Now, suppose if at all I give you something like this, it is sp3 hybridized, you are having like this sp2 hybridized, and I'm giving you something like this sp hybridized. So what about bond energy? As the percentage S increases, you're going to have higher percent or else higher bond energy, right? So make sure all of you are writing this. Now this factor which is there, it is going to affect the bond association energy of only second period elements, that too when they are singly bonded. Okay. Other than that, no effect for this. You know? So we are saying it affects the bond energy of singly bonded second period elements. Singly bonded second period elements. It does not affect any other period element, right? So their bond energy, that means I'm talking about singly bonded second period element. Right? So their bond energy is less than the expected value or else the expected order. Let us see few example here. Suppose I am taking one example as F2, Cl2, Br2 and I2. I know what is going to be the bond length order, definitely like this only. This order is fine. So based on that, we might think that the bond energy has to be like this. Bond length increases, bond energy decreases, but it is false, right? Now what is happening here is we are having fluorine and chlorine. The electron density, like the number of lone pairs which are there, they are same, right? Only thing is out of fluorine, chlorine, size of fluorine is less. And because of that, electron density will be high on this, right? Charge density which I am talking about. So the electron density is going to be high here. And if that is the case, then you are having more lone pair repulsions. And because of that, this bond becomes weaker. So what is the overall order which we are going to get here? Overall order in this case, basically you'll be seeing that, and this is overall order for bond energy, and this is important also. You'll be getting Cl2, Br2, F2 and I2 like that. That's where your fluorine is placed. Okay. So please do this. Then I am writing few example which you need to do. Oxygen, oxygen, sulfur, sulfur, nitrogen, nitrogen, phosphorus, phosphorus. Then you are having carbon, carbon, silicon, silicon. Do this. Yes, are we done writing? Yes. In this case, oxygen belongs to second period, right? So for second period, lone pair dominates. So basically we'll be saying the bond energy for them will be lesser. You're also having one lone pair. Bond energy for phosphorus is going to be more. Here, no lone pair of electrons. 14th group, right? So basically we just have to see bond length increases, bond energy decreases based on that. Getting it? In fact, if at all I would have written like this also, suppose I would have given you carbon, carbon, nitrogen, nitrogen, oxygen, oxygen, fluorine, fluorine. So here you are able to see more lone pair as they are increasing, more lone pair repulsion. So basically bond energy order would be like this. Getting it? Here you can't apply delta En because it's same, 0. For all of them, bond order is also same. So only factor which is remaining is they are second period elements. Based on the lone pair repulsion, you can easily identify this. Okay, are we done? So this bond parameter is also completed, right? Understood now? There is no confusion in these problems to anyone. Okay, good. Now let us go for understanding hydrogen bond. And at present you just try to understand, then I'll be giving you the definition, don't worry about it. Okay. Now let us try to see what is this hydrogen bond basically. Suppose I have taken a sample of HF, right? When I say sample of HF, that means I am having more than one molecule of HF in that container. That's what we understand, right? Now, you are having this HF, there is electronegativity difference, right? So because of that, are you going to have delta plus here and delta minus here? Now, in the vicinity of this HF molecule, there will be another HF molecules also. So let us say there is another HF molecule. Are you able to see lone pair here? Here also I am writing another HF. Here it will be delta plus, right? Now what happens, because of this delta plus development on this particular hydrogen, this is going to attract this lone pair of electrons on the other atom of fluorine, which is not bonded to this hydrogen, right? And this interaction which you are able to see in this, around 2 to 10 kilocalorie per mole of energy is liberated, and if that much amount of energy is liberated, we call it as hydrogen bond. Mind well, it is not any covalent bond, right? It is sheer attraction or interaction between these two, right? Okay. Now the prime requirement for this hydrogen bond formation is your hydrogen should be connected to more electronegative atom, where the electronegativity is greater than or equal to 3 minimum. That is the requirement, right? And you should have another atom which should have, that should also be electronegative, and it should have a lone pair of electron, right? Here I have taken HF sample only, right? Sometimes it may happen you can have any other species in water, so you can have this changed. Getting it? So here I am going to write down, when hydrogen atom is bonded to more electronegative atom like fluorine, oxygen, nitrogen in general, then partial positive charge develops on it, due to which it attracts lone pair of electron present on non-bonded polar atom. So you can have non-bonded polar atom as fluorine, oxygen, nitrogen, chlorine. In general, I am saying, if in this interaction, energy released is between 2 to 10 kilocalorie per mole, then it is termed as hydrogen bond. Now you must understand one thing, this is in general, on an average this much amount of energy is released. Sometimes if very strong hydrogen bonding is happening, this value might also be crossed. Okay, we'll see that one example, don't worry about it. Okay. So here I am writing, you should have AH. What is this? A is telling you? A is telling you that it is electronegative atom. Right? This is electronegative atom. For this, what is the requirement? Its electronegativity has to be greater than or equal to 3. You can have here nitrogen, fluorine, oxygen, sp hybridized carbon. You can have CCl3, you can have CF3 like that. And here, basically, lone pair of electron containing electronegative atom, and which is normally fluorine, oxygen, nitrogen and chlorine, normally I'm saying. And here, if 2 to 10 kilocalorie per mole of energy is liberated, I call this as to be hydrogen bond. Please make sure that you are writing it. Yes, written all of you? Okay. Now, I'm going to write down one thing here. Strength of hydrogen bond, it basically depends upon delta En of this AH bond, and this is a more dominant factor. That's what I'm putting a tick mark, double tick mark, right? And directly proportional to basic strength of this B. B is this one which is sharing its lone pair of electrons. Now try to understand this. If higher is the electronegativity difference here, then more delta plus on this, and more easily it is able to attract the lone pair of electrons from here. That's why the strength of hydrogen bond is more, right? Now, the thing is, this is the more dominant factor. If this factor becomes same, then you check by this basic strength. Now the thing is here, are you able to see hydrogen is attracting the lone pair of electrons, right? So this particular B should be a good Lewis base. That means it should be happy to share its electron, easily able to share its electron, right? So if at all it is easily able to share its electron, then its basic strength is going to be high, and because of that, hydrogen bond strength is going to be more, because more force of attraction there. Getting it? So let us see one question based on that. Arrange the following in decreasing order of strength of hydrogen bond. So suppose if I give you FH, F minus, FH, F, OH, O, OH, N, NH, N, NH, O. You have to arrange them according to the decreasing order of the strength of hydrogen bond. Take some time, try to do it. You must try all the problems, okay? Worst possible scenario is you might land up in some wrong answer. That's okay, but at least you gave it a try. Yeah, you'll understand where is the misconception which you are carrying. So first thing what we are able to see is delta En. Based on the delta En, you will be able to realize first and second, they are more than third and fourth. And then third and fourth, they are greater than 5 and 6. This much is clear to all of you. First and second is going to be more than third and fourth because delta En for FH is greater than delta En for OH. Is this much digested? Now, next thing is if delta En becomes same, you need to check by the basic strength. Out of F minus and F, which one will be a better donor? Which can easily share its lone pair of electron? In F minus, already more interelectronic repulsion. People are already fighting among themselves. So they'll be able to share that or else give the lone pair of electrons, right? So in that case, first greater than second. Now for this delta En is same. Out of nitrogen and oxygen, which is less electronegative? Nitrogen. So if it is less electronegative, then it will be able to share its lone pair of electrons. So that is the reason I'll be able to say 4 and then 3. Then here again it is 5 and 6 because delta En factor is same. All you need to see is whose electronegativity is less. More electronegative, it will tend to hold on to its electron. Na? It will not be able to share it. Okay. I hope it is clear to all of you why this order. Yeah, fine. Now let us go for hydrogen bonding in some species, and this is going to be important. First one is we are going to see the case of HF, H2O and ammonia. Now let us see for HF. For HF, let us see how many hydrogen bond it will be able to make. So you know whichever is in lesser amount, it will be in more demand. That's what is the concept of limiting reagent, right? So basically for hydrogen bond, we require hydrogen and we require lone pair of electrons present on the atom, right? But out of these two, that means whichever number of hydrogen or else number of lone pair of electrons, whichever is less, it is going to decide how many hydrogen bonds are going to get formed. Here you are having one hydrogen atom. Here you are having 3 lone pair of electrons, right? So out of these two, which is lesser, hydrogen. So hydrogen is going to decide how many hydrogen bonds. So for the formation of hydrogen bond, one hydrogen just require one lone pair of electron. So basically, from the other species in the sample, it is going to attract like this. Now, also you are having 3 lone pairs. Out of that, one lone pair will be attracted towards the other hydrogen. Are you getting this? So basically, are you able to see one HF made 2 hydrogen bond? And I have written like this, it doesn't mean it has got a linear structure because hydrogen bond, lone pair will be in particular orbital and they are going to be directional, right? So let us see the structure of them. HF, if I see, so basically, this is the lone pair of electrons which are being attracted by this HF. Are you able to see? There is a direction of this particular orbital. And from that, the lone pair which are there, they are being attracted towards this hydrogen. Then again, you are having this fluorine. So it is having lone pair of electron. It is going to attract this HF. Right? You're going to have like this and this continues, right? So are you able to see this is a zigzag structure? Zigzag structure which exists in their solid state. So from there we are confirming that it is able to make only 2 hydrogen bonds. Okay, please write this down. Then we'll proceed further. Write this and let me know. Its structure is not linear. Do remember that. It is zigzag structure. In a particular direction, it is getting formed. Now, second one is H2O, right? In case of H2O, are you able to see you are having two hydrogen atoms and you are having two lone pair of electrons also. So basically here nothing is like limiting. Here they are equal. So there are like equal probability of hydrogen bond here. So basically you will be having one lone pair requires one hydrogen. Here also one lone pair requires one hydrogen. Are you able to see that? And then again one hydrogen require one lone pair of electrons. Here also it requires one lone pair of electrons. Are we able to see this? Right? So basically you will be able to see one water molecule is making four hydrogen bonds and basically it will be like tetrahedrally surrounding it. And this phenomena only leads to, hollow spaces in ice. So that's the reason ice floats on water, no? Because if you might have seen when you put the, you might be filling up the tray of for ice, you'll be filling the water and then you'll be putting it in freezer, right? But if at all, when you take it out after some time, that ice, what it has been formed, it might have risen up in the height, right? So what is happening there? You didn't do anything, right? Mass you didn't change. You just kept the same amount of water in that ice tray. Mass was same, but volume increased. Are you able to see this one? Because of the hollow spaces of the hydrogen bonding, due to the hydrogen bonding. And that's the reason density becomes less. So you are able to see that increase in the size because of that volume expansion, because of the hollow spaces created by hydrogen bond, right? So ice floats because it becomes less denser on becoming solid. So please write this. Then for ammonia, are you able to see this is the reverse scenario? You are having three hydrogen atoms and one lone pair, just the reverse which you had in HF. You had three lone pairs there and one hydrogen. So basically who is going to decide now? It's the lone pair who is going to decide. So how many hydrogen bond we are going to have? One lone pair requires one hydrogen atom. Similarly, one of the hydrogen atoms can bond with what? One of the lone pair here on the nitrogen. So basically you are going to get two hydrogen bonds here. Getting it? Please draw this, then we'll proceed further. Yes, hopefully everybody has written this. Now, if at all I write HF, ammonia and water, let us see how much is the bond energy associated with this hydrogen bond. Basically, are you able to realize that AH in these cases are different or not? AH. In one case you are having NH, in one case you are having OH, like that you are having, na? Hydrogen is bonded to different electronegativity of the atom, right? Now in that case, when they enter into hydrogen bond, so basically the energy which is liberated in that process is going to be different, right? So in this case, it is seen, it is 10 kilocalories per mole. Here it is 3 kilocalories per mole. And here it is basically 7.5 kilocalories per mole. Able to understand what I've written here? So when they enter into hydrogen bonding, so basically this much amount of energy is being released. And it is being justified because the delta En is maximum here. And after that you are having for water and least is in case of this. Now if at all I write down number of hydrogen bonds made per mole or basically by one molecule of it, are you able to see 2 here and 4 here? So if at all I have to arrange them according to the strength of hydrogen bond, simply based on the energy data, bond energy data, I'll be able to arrange them. So HF being maximum, then H2O, and then you are having NH3. This you understood? Strength is shearly based upon how much energy is being released when they entered into the hydrogen bond formation. Now there is one more terminology which is basically extent of hydrogen bond, and that is given by strength of hydrogen bond into the number of hydrogen bonds formed. So if at all I have to compare for HF, NH3 and H2O, right? Extent of hydrogen bond. So what is the strength? First of all, it is 10. How many hydrogen bond it is making? 2. So are you getting 20 kilocalorie? In case of ammonia, what is the strength? 3 kilocalorie is getting liberated. 2 hydrogen bond means 6 kilocalorie. For H2O, are you having 7.5 is the amount of energy liberated, that is the strength, and number of hydrogen bond is 4, you'll end up with 30. Right? So for extent of hydrogen bond, the order will be H2O, then you are having HF, and then you are having basically ammonia. Right? And depending on this extent only, you'll be having different physical properties depending. That means boiling point, melting point, viscosity, vapor pressure, volatile nature. Everything depends upon what is the extent of hydrogen bond present in the species. So you're having here H2O, then HF, and then NH3. So this is important. So you can directly remember the orders here. For strength, simply based upon how much energy is being liberated. For extent, we are considering energy and also basically how many hydrogen bonds formed. I'm writing a note here. All the physical properties of a molecule like boiling point, melting point, right? Then you are having viscosity, vapor pressure, etc. depend upon extent of hydrogen bond. Please write this down, everyone. I think from here it is remaining. Please write it, then I'll scroll it up. Yes, hopefully people have written up to certain extent. Write this, then we'll proceed further. Finished? You need not worry about the data. The thing is, this data is only to make you understand. Okay? Nobody will be asking you in the examination. They'll be asking you directly the orders. Getting it? Yes, finished? Now, second one is chloral hydrate. Now, when it comes to chloral hydrate, basically I'm writing CCl3 CHO dot H2O. In this case, I'm having CCl3. You're having H and double bond O. Now, if you remember how this hydrate will be formed, do you remember that this is a carbonyl compound? You're able to see C double bond OH, and for them characteristic reaction is basically nucleophilic addition reaction. So here it is a nucleophile which is going to attack at its delta plus center, which is this carbon, and this is going to move like this. So you are going to have CCl3, OH, OH and H. This is what is chloral hydrate. And if you remember something, that on one carbon, sp3 hybridized carbon, we say if at all there are two OH, it is very unstable, right? Normally we tend to remove H2O from there. It is not possible to make, like, keep them there because of the lone pair repulsions, right? So basically here it is stable. You are able to see this equilibrium is more in the forward direction as compared to backward direction. What is the reason for that stability? Here I am writing this particular, two carbons are there, na? And here you are having Cl, Cl, Cl. Are you able to see I have drawn these two carbons? You are having Cl3 on the other carbon, two OH here and one hydrogen. So basically intramolecular hydrogen bonding takes place between them. Intramolecular, within the same species. So intramolecular hydrogen bond between them will make this species more stable, right? So chloral hydrate do exist. Okay, so please write this down. Yes, are we done writing? Then third one is KF reacts with HF to form KHF2, but the same type of reaction, does not take place with any other group 17 hydroacids, right? Let us see why. Hydroacids means HCl, HBr, HI, HF, right? Having hydrogen and the other non-metal here. So if at all I am having KF, it is said it is able to react with HF to give you KHF2, right? Basically this exists as K plus and HF2 minus, and then this HF2 minus, basically it is a very strong hydrogen bonding is happening like this, and the energy liberated is almost 40 kilocalorie per mole because of the strong hydrogen bond. Remember I told you that some of the, like, if at all very strong hydrogen bonding is taking place, then the energy can even cross that 10 kilocalorie level, hai na? 2 to 10 kilocalorie we are saying, na? More than that is also possible, but here only hydrogen bond, right? Getting it? So that much is the strength which is almost comparable to the strength of a covalent bond, right? With other hydra acids, this kind of interaction is not possible. That means the hydrogen bonding is not taking place like this. So that is the reason it is not getting formed. Please write this. Then I can also write acetic acid dimerizes in non-polar solvents. So acetic acid, non-polar solvent like CCl4 is there, C6H6 is there. So you're having acetic acid like this, C double bond O, OH, CH3. Then COH, you're having CH3 double bond O. So are you able to see this is the hydrogen bond which gets formed between these two molecules? That's why a dimer. So very strong hydrogen bonding takes place in case of acids, right? And non-polar solvent means CCl4 is there. You can have basically C6H6, like that, few examples. Please write this. I hope we are done writing it. Let me know. Okay, good. Now let us see types of hydrogen bonding. And there you are going to have two types. One is intermolecular hydrogen bonding. Another one is intramolecular hydrogen bond. Now, when I talk about intermolecular, inter is always between two, right? Like in the school competition, intra means within the same, right? So, inter is intermolecular hydrogen bond means between the two molecules who are having hydrogen bond. Intramolecular means the condition for hydrogen bond formation is present within the same molecule, right? So, within the same molecule, hydrogen bond is going to happen, right? So, here, hydrogen bond between two molecules, and here hydrogen bond within the same molecule, right? For example, we can take para-nitrophenol, and here we can have orthonitrophenol. So in case of orthonitrophenol, are you able to see the condition for hydrogen bonding? It is present here within the same hydrogen bond, and they're nearby. So intramolecular hydrogen bonding is happening. Hydrogen connected to more electronegative atom, which is oxygen, and you are having a lone pair donor atom there, that is oxygen. Then in intermolecular, you'll be having this as OH, NO, double bond O. The other molecule like this, OH, hydrogen bond can form here. Similarly here, NO, double bond O. So are you able to see the hydrogen bond here? And this is basically intermolecular, and that is intramolecular. Please write this down, then we'll proceed further. Okay. Now the thing is, because of intermolecular hydrogen bonding, I'll say here that the boiling point is going to be more. Why more? Because we are taking the sample of this paranitrophenol. More than one molecules are there, right? So between them, if intermolecular forces of attraction is high, then you are supposed to provide more amount of heat so that they go into the vapor phase. Because boiling point means, what is boiling point? You are having a liquid and you are trying to give, like you are heating it so that it enters into the vapor phase. So if the liquid molecules are holding each other nicely, then you have to supply more heat to overcome that force of attraction. That is the reason boiling point over here is going to be more. What about this? You are having the sample of orthonitrophenol. So basically you are having their molecules, but they are content among themselves. They are not bothered about their neighbors, right? So there is less intermolecular forces of attraction between them. So because of that, less amount of heat and they'll boil up. So you're having here boiling point less. Now, if boiling point is high, I say that the vapor pressure is low and the volatile nature, or that is volatility, that is low. Here it is the reverse. Vapor pressure is going to be high and the volatility is also going to be high. Try to understand this. Here boiling point is less. That means they have the tendency to go into the vapor easily. So if more vapors, more easily vapors are getting formed, more volatile nature or volatility. And if at all more vapors are getting formed, so those vapors are going to apply more pressure onto the surface of liquid and hence high vapor pressure. And the reverse for this case. Right? Hopefully this is clear to all of you. I hope there is no confusion now. Any doubt remaining here? So with this, our chemical bonding chapter gets over. Okay? That means is enough. Yeah, I'll tell you, Ashfaq, don't worry. See, somebody has asked me that doubt. I'll tell you. See, in case of HF, you see here, you are having 3 lone pairs. You are having 1 hydrogen, right? Now the thing is, whichever is lesser. For the hydrogen bond formation, we just require 1 hydrogen and lone pair should be there. That is a condition, na? Hydrogen connected to more electronegative. Out of these two, number of lone pairs and hydrogen, which is less? Hydrogen is less, so it is going to decide. It is going to decide in the sense, from one molecule, only 1 hydrogen can be available, right? So that is going to attract the lone pair of electron from the other one. So this is 1 hydrogen bond done. But in the same molecule, you are having 3 lone pairs. Out of that, only 1 lone pair is going to attract other hydrogen. So with that respect, we are saying. Is it clear, Ashfaq? Yes? Now, coming to ammonia, it is a reverse scenario. 3 hydrogens, 1 lone pair. So who is going to be deciding factor here? Lone pair. And 1 lone pair requires only 1 hydrogen for the hydrogen bond formation, right? So basically, here it can attract 1 hydrogen atom. And here, 1 hydrogen is also there, na? So from other one, from nitrogen, it can attract lone pair, na? Able to see this? That's how too. Got it, everyone? Good. Fine now. So with this chapter is over. So let us see what is the next chapter which is coming up. So till now, so fine. You people revise it. Gagandeep, I can understand better. The thing is, you are having this video available with you. You can check it once again, right? Not an issue. Okay. And the thing is, wish you all a very happy Dussehra. Okay. And enjoy the festival and wish you all the best for the test also. Yeah. Thank you and have a nice day.